Recording?
Yes.
Wonderful. So, I don't believe I have any announcements to speak of today pertaining to the course material. However, if you haven't heard, yesterday in the afternoon, early afternoon, we lost our beloved monarch, Queen Elizabeth II. It's kind of funny because I was actually submitting my final copy of my thesis to the university archives, thus completely completing my PhD process at almost the exact moment that she passed. Thank you for your applause for finishing my thesis that was keeping the Queen alive.
We said that alone because one of our lectures ended. That's one.
Oh, yeah? Maybe. Anyway, I think it would be a very nice and appropriate thing if, at the moment, if we had a moment of silence to commemorate the passing of so great a monarch.
And your thesis.
And, well, mostly QE too, but the respectful thing to do would be to stand for a moment of silence. We'll start it now. God save the King. So, yeah. All right. Anyway, that's enough time wasted. What is all this time wasting? Jeez. Commemorating the death of beloved monarchs in class. What the heck is he thinking? I mean, is this thing even on? You know what? Be that way. Anyway, so, right, let's continue on from where we were. So, previously, we had not got very far into our discussion of algorithms, but we had some interesting ideas presented. We had just talked about the array, which is, of course, the simplest of all data structures, and we shall shortly sort out linked lists. Any questions about anything before we get beginning? Good. So let's discuss the singly linked list. This is where pointers come back to rear their ugly heads once more. So, a singly linked list, which is sometimes variously just called a list, is a linear collection of nodes. You'll notice we have a very brief piece of code on the side here to describe the structure of such a node, assuming that we are implementing these nodes as classes in Python. They just came from Python classes. Java. Each node has a value and a pointer to the next node in the list. It's actually possible to bundle entire record entries in this manner. It doesn't just have to be a single value that's stored in the node. You can store as much stuff in the node as you want, but this is the simplest working example. The head of a list is the first node in the chain, and the tail of the list is the last node in the chain. The tail of a singly linked list points to null. So, you guys all remember Haskell from last year, right?
Yeah.
Very well.
Good. You remember the cons operator?
No.
The list constructor operator? Colon? You know, you, yeah, okay. So you have an item, colon, list, right? You can do like x, comma, open brace, or the empty list, that type of thing. This is like making x into a list, the operation, right?
Yeah.
This is null, right? This is make it a pointer to the next, right? That's what that operation does. In Haskell, it really should say something to you that everything in lists and arrays practically don't exist, right? Lists are a very, very, very highly useful thing. Let's talk about doubly linked lists. So what is the key flaw of the singly linked list? Anybody? Yes.
That's me, right?
That's you.
Okay. It has to, in the single linked list, you can only go in one direction, and you want something to go in one direction.
Absolutely. In a singly linked list, they are traversable in only one direction. If you have a pointer to any node in this list, you can only get 2 nodes further down the list. This is sometimes a problem. It can be inefficient. We're going to have a slide on comparing arrays to lists, so I'll save that for them. But the doubly linked list corrects the flaw in the singly linked list by having pointers which point backwards up through the list rather than having them all travel in only one direction. So we now have a list which is traversable both forwards and backwards. This is, this is good. Basically, in a singly linked list, let's imagine you have a relatively small one, right? Let's say we have, we have a pointer to 3, and we want to find the previous element in a singly linked list. How much time does it take, right? Worst case scenario, the number of nodes in the list minus 1, right? Versus, if it's a doubly linked list, then that gets turned into constant time, yeah. So, this is yet another example where we spend a little bit of memory to be able to get a lot of runtime. Make sense? Any questions so far? You, sir, in the NASA t-shirt.
So how does the node previous connect to with the previous item? Does it point to the key directly, or it points to the node?
So, that really strongly depends on the implementation, right? If you're talking about a C implementation, and presuming the key is the first element of the struct, in C, the first element, it's kind of like arrays, where the first element of the array is also the thing the array pointer points to. The same thing applies in structs, where the first field in the structure is the thing that is pointed to by the struct pointer, right? So, in a sense, both. It depends. It depends on the implementation. It depends on the language of implementation. Question?
Is it possible to construct a linked list so that it contains multiple data types?
Is it possible to? Well, yes, absolutely. That's how Python does it, for example. A list in Python can contain as many different data types as it likes. In general, certainly, for reasons of, with an array, we need to have a monotyped array to be able to calculate the memory address offsets which allow us to access indexes. Because we're dealing with nodes here, we are lifted from that constraint. We no longer have to have a monotyped list for the purposes of maintaining the integrity of index lookup, right? That being said, if you look at a language like Haskell, lists are monotyped, right? So, again, depends on the language of implementation. I feel like I'm going to be saying that a lot in this class. It depends on how you're implementing it. Question?
Besides memory, like you just talked about, is there any other reason you'd use a linked list over a normal array? Or are we going to cover that later?
We are very strongly going to cover that in like 1 or 2 slides. It makes certain operations very fast at the expense of certain other operations, but in general, it's a good deal. So, good. Doubly linked lists are one of many examples where, yeah, I said that already, and yeah, good. So, I just want to make one brief note. Many of the data structures that we're going to talk about, even later on in this very topic, are going to be constructed, using linked lists, like arrays, linked lists. In this lecture, we'll actually talk about constructing things with either arrays or linked lists. Later on in the course, we're going to begin to start assuming that we've just chosen between the two of those correctly and abstract these details away so that we can focus on more interesting parts of the algorithm when we get there. So, there's a very good reason that this is the very first thing we're covering in this class. It's because it's absolutely fundamental to many of the data structures that we're going to be talking about. For example, when we get to graph theory, what is a graph? It's a bunch of nodes with a bunch of pointers. Basically, if you turn the next thing here into a list of pointers rather than just a single pointer, then you've got a graph. So there you go. The concept is applied. Does that make sense? I know that's a little jumping ahead. So, let us examine some operations over linked lists. We shall examine searching, insertion, and deletion. Do you guys need me to define those for you? You guys okay with knowing what those operations do? We should probably go over it. So, to search is to take a look through the linked list, examining the things to see if it's equal to a thing you're looking for. If so, you return either the index to that thing or just a Boolean true false. Insert, given a linked list and a new node, we wish to insert that node into the list. And deletion, given a pointer to a node in the list, we wish to remove it. Note here that we're talking about deleting via pointer, not via index, right? But if you wanted to write an algorithm to delete via index, that would also be the process is almost identical. All you need to do is perform the search operation, and maybe you've written the search operation to return a pointer to the node that you've searched for, right? All you have to do is slap a search operation on the front of the delete operation, and there you have it, delete by index, right? FYI, pointers are assumed knowledge in this class. If you didn't get that impression already, there it is, black and white, clear as crystal. So if you don't know pointers, go hit the books. So, we linearly search a node, we search for a node with a value k by linearly traversing the list L. That is to say, over a linked list, linear search is what you got. In order to use some more advanced searching technique, like binary search, for example, you not only need, and I kind of talked about this at the end of last class, you not only need the data to be sorted, which is of course a condition that we're not guaranteed with just a general linked list for obvious reasons, but you also need constant time lookup, right? If the lookup is a linear time operation and the search is a logarithmic time operation, which of the two of those will come to dominate the runtime of the algorithm over time? Obviously, yes. So, it's not worth it, basically. Pardon me. And once we have access to pointer technology, there are much more interesting ways that we can construct searching algorithms than binary search anyway. Like, for example, binary search trees. But anyway, this is important nomenclature. Traversal, or walking a data structure, means to follow the node pointers from node to node to accomplish some goal, such as finding a specific element. So, if I'm walking the linked list, that means I'm going through it following the pointers down, which, as you can see, list search on L and K, we set X equal to the head of the list, assuming that that has been made accessible by the list class as a parameter or a, what do you call those in Java when you have like a variable inside of a class? Does anybody know the Java nomenclature for that? Instance variable? Okay. I'm just going to call it a variable. Or a member. I think member is good. Anyway. While x is not equal to nil, that is to say, while this pointer does not point to nothing, and x.p is not equal to k, we set x equal to the value of x's current next pointer. Then, at the end, regardless as to whether we have found nothing or we have found it, we return x. So, in the case of failure of search, what is the return value of this algorithm?
Nil?
Yes, nil or null or whatever your non-value is. 0 pointer. Make sense? So this is pseudocode, by the way. You can certainly tell that because, like, small caps case is not valid in any programming language that I'm aware of. So, list insertion. This algorithm inserts a new node x at the head of list L. This is like your basic prepend operation. Why would we want, so assuming that this is a singly linked list, why would we want to prepend as opposed to postpend? Append, there we go. Why would we want to prepend as opposed to append?
So you don't have to go through the entire list every time you want to add an element?
Absolutely. Prepending on a singly linked list is a constant time algorithm, whereas appending on a singly linked list is a linear algorithm. Good, because you have to go through each node to find the end, because you have to walk the list to find the end of the list. Unless you've done some bookkeeping on your data structure and it knows where its tail is. That's one way that you can get away from it. So, if you add a variable to the class and update that variable to, when the tail of the list is modified, update where the tail is, keep a pointer to your own tail, then you can append or prepend in the same amount of time because you know where the tail is. But unless you do that bookkeeping, you don't know where it is. Right?
That's a third year.
What?
They have to do that in third year in operating systems.
Ah, there you So there you go. I'm giving you advanced pointers, so to speak, on how to pass your third year classes. That's pretty good, yeah. Yes. So, insertion, anyway. So, we have L and X again. X.next is equal to L.head. So, X in this case is the node that we're inserting. So, we're assuming that the node has been created, the malloc has been called, and it has been placed somewhere in memory. We make its next pointer point to the old head, and we, assuming this is a doubly linked list, we set the previous pointer of the current head to the new one we're inserting. We set, that is to say, if that head pointer is not nil, and then we set the head equal to x and x dot prev equal to nil, right? So that sets x up as the new head. Make sense? Any questions? Good. So let's talk about deletion. If we wish to delete a node x from a list L, given its pointer, we first check to see if it's the head of the list, right? This one's a little bit tricky because you have to have different behavior based on whether the node is at the beginning, the middle, or the end of the list, right? Because you have to be able to put the nil or the null pointers in wherever you want. I might just switch to saying null pointers. In case it wasn't sufficiently clear, nil and null are precisely and exactly the same concept. They are synonyms, you might say. So, if x dot previous is not equal to nil, then x dot previous dot next is equal to x dot next, right? So we take the thing that x is pointing to previously, we take its next, and rather than like x dot prev dot next will initially be pointing to x, but we want it to be modified so that it's pointing to the thing x is pointing to next, right? Maybe I should draw it. I think drawing it would be good. I think we've reached that point. So, if we have x, y, and z, this will be stuff on, like, this will be previous and this will be next, right? So, right? So, we want to delete y. Operation number 1. This guy gets blown out and given the value stored here. So here we go. Right? Next operation. This guy, currently pointing to y, we want him to point to whatever y was pointing to as previous. Right? So we overwrite this pointer, bop him over here, right? Now we're in this interesting situation. From the perspective of the list itself, y is no longer in the list, but y still thinks it's in the list, because it's still pointing to the things that were correct previous to deletion. But the integrity of the list is not impacted if we simply delete and deallocate y as a node. This performs deletion. Any questions? Yes?
So whenever we want to insert and delete and we're not dealing with the first and last element, we can only do that with the doubly linked list.
Well, let's examine the process with respect to a singly linked list. So, x, y, and z. So x points to y points to z, right? If x, so if we want to skip y, we just take the value here and write it there. So we get that, right? and then it's safe to delete it. Now, if we have, you know, let's take, for example, the case where y is the last element, right? So y is pointing to null, right? If you try to follow this pointer, what will you get? In C, what will you get?
Why?
If we try to follow this pointer, pointing to null in C, what do you get when you dereference a null pointer in C? Not in C. C doesn't have exceptions, remember. You get a type of error code, there's a specific name for it. Thank you! It's a segmentation fault. This pointer points to invalid memory that's not been assigned to your program. If you try to access memory that doesn't belong to you, you get a segmentation fault. So that, this algorithm cannot be applied if y is the end of the list. You have to check to see if y's pointer points to null first. That's what the if statement is for. So, if this points to null, you just make this point to null instead, and then you delete it anyway, right? But it's very important that we write our algorithms in such a manner as to not produce segmentation faults. Does that make sense? Does that answer your question?
So basically, either we use the linked list or single linked list, we can perform the same type of insertion and deletion.
Yes. Insertion and deletion honestly do not change that much between singly and doubly linked lists. Doubly linked lists, you just have two sets of pointers to keep track of instead of one. But it's really, it's not too bad.
And therefore, which list is more, in terms of efficiency, is one more efficient than the other?
Doubly linked lists consume slightly more memory, but can do certain operations a heck of a lot faster. So it's again the memory time trade-off. Sound good?
Yeah, thank you.
You right there. You're gonna have to shout, yeah.
Okay. So when we've gone around the y value in the list, like it's not really gone. It's still pointing to things. It's just that we can't access through it through the list. So isn't it like still taking up memory or something? Is there something else we have to do to deal with that?
The final step, which is not placed here, is the deallocation of the node. Yes.
It's language specific though, it's a Python.
That's precisely the case. So, because this is pseudocode, it's trying to avoid those types of language implementation details, right? Like, I'm going to refer to C a lot, right, just because it's, frankly, the language I'm more familiar with. But in C, you would require a manual free operation to free the memory associated with that node. In a language with garbage collection, these types of nodes, which nothing points to anymore but are still allocated, are periodically collected up by the garbage collector and thrown out of existence, right? So I believe Java has a garbage collection.
It's terrible,
So,
but it does have it.
yeah. I think Java famously has garbage collection. It was one of the first languages to have garbage collection, I think. So in Java, you can just leave that node there and a sub-process will come along and clean it up for you. The Java garbage collector will come along and clean up your whoopsies for you. But that type of nonsense is not tolerated in stricter languages, like C. Make sense? There was a question up in this region. Oh, okay. Question here?
Yeah. So since a double linked list points in two directions, is there a null node on both ends?
That's correct, yes. The previous pointer of the head node also points to null. So we would have a similar situation to this at the head of the doubly linked list, and as you can see, that's indicated in the algorithm. Question?
Wouldn't it make it easier to search the list if you connect to the head and the tail?
as a matter of fact, it would. So, let's just throw one further fly in the ointment here. One of your colleagues very correctly and astutely observed, could we not improve the efficiency of searching if we connected the head, connected the previous pointer of the head to the tail and the next pointer of the tail to the head? And the answer is, what you do by doing that is create an entirely new data structure called the circular list, sometimes also called a ring. So, so obviously if we were to go through these types of operations over a circular list, this case here where we have to check explicitly for null pointers won't happen in theory, because a circular list in theory doesn't have any null pointers. Yes?
So wait, if you do the search algorithm that you said for the other linked list on the circular list, it would cause an infinite loop though.
Yeah, you'd have to do, so one of the things about circularly linked lists is you have to do bookkeeping, so a little bit of extra bookkeeping, for example, to find your entry point into the list. Like, this thing's still technically going to have a head, but the interesting thing about a circular list is a pointer to any node in this list behaves in the same manner as a pointer to the head, right? So in theory, the thing's searchable from any point. You don't have to start at the head. You can just follow it, wrap it back around. But yes, if you don't keep track of the node you started on, right, and probably its memory address, then yeah, if you don't find the thing you're looking for, you'll just keep searching it until the cows come home. Yes?
On the previous slide,
Yeah?
for the Exxon Festival's meal, the night meal, and then you set the pointer for the previous one to the next one, would you check the next one with the meal?
Let me take a look. So, so your question has application. It might be that there's an implicit assumption in this algorithm that the linked list contains at least two elements, right? Like, in theory, this algorithm certainly assumes that the list contains at least one element, right? So, you know, if we have a list, right, with one node, which points to null on either side, right? To delete it, we simply free it and return a null pointer. But yeah, like there are going to be a lot of edge cases in these that, you know, we aren't maybe. There are going to be implicit conditions on these, but I may not have answered your question correctly.
If you have like the X and then you have the Y, you don't have the Z, you have to check to put this code right now, X.next because X.next, that assumes it's three elements.
Yeah. For deleting the last node? So we want to delete Z, and Z is the end of the list? That's your question? Yeah, sort of regardless as to what the slides say. Yeah, to delete Z, we have to take this guy and assign it to null, right? But because this is null, we don't have to worry about reassigning the previous here. So this just gets set to null, and we delete it, right? Sort of regardless as to what that says. Any other questions? Wow, we've spent most of the class on linked lists. All right. So, Circular lists. Good. Quickly. Trade-offs for linked lists versus arrays. Linked lists are better for dynamic data. Arrays are better for static data. If the data is not moving around very much, then an array is going to be more efficient a lot of the time, if only for the fact of constant time lookup. If your data is mutating frequently, the fact that you can insert and delete nodes from it, if you have the pointer in constant time, that's very, very good. Because, you know, if you have an array, right? Let's say we have an array, and we want to delete this element, and this is the tail, right? In order to actually perform the deletion, you don't touch that part, but you copy all of these elements into the space, and then you have a space at the end which is no longer used, which you can, you know, realloc the array if you really care to delete that little end piece. But each one of these is a copy operation, and in the worst case scenario, that takes the whole length of the array. So deletion is linear. Expensive, not in comparison to some things, but in comparison to constant time, yes. Good. So, one of the main benefits of an array is that indexing is constant, and indexing on a list requires traversal, which is a big O-N. For a linked list, expansion only requires allocating new nodes, whereas an array expansion may require copying the entire array into a new memory chunk. Do you guys remember that? Maybe? All right. Very quickly.
Isn't that realloc?
So, if this is your memory, right? Let's say that your array is hanging out between two pieces of used memory. The kernel is smart enough, if there's extra space after it, to try to use that extra space. But if it's blocked for some reason, then if you try to expand it, it will just have to copy the whole thing to new memory. Right? Make sense? So, dynamic array operations might be expensive, whereas with a list, all you need to do is find space for one more node, and you've got a pointer to it. Question?
Is there any advantage other than for static data for arrays?
They're simple. You don't have to work with pointers. Right? So, most of the advantages of one versus the other are tied into the static versus dynamic thing. But arrays are actually a little simpler to work with. Yes?
Is Python lists a linked list or an array?
I'm not precisely sure, but I'm almost dead certain that it's a linked list.
Yeah.
Yeah? Yeah. I'm inclined to think that they wouldn't call it a list unless it was a linked list. And I think that's applicable to most languages. Any other questions? Yes?
Have you ever practically used a linked list in a real program?
Most of the programs I write are for tests for people, so I'm probably not the best person to ask.
That being said, I have.
You have?
Yes.
Okay, cool. Can you summarize it in 15 seconds?
Probably not.
Okay, all right, fine.
Not to mention it's also protected by confidentiality agreements because it was for a job.
So you're not going to tell like this class of like 200 people? Yeah. So linked lists, deletion and insertion are faster in lists, slower in arrays, in summary. Good. So, abstract data types. An abstract data type is a mathematical model for data types where a data type is defined by its behavior or semantics from the point of view of a user of the data, specifically in terms of possible values, possible operations on this type of data, and the behavior of these operations. I have just described object-oriented programming. The abstract data type defines the logical form of the data type. Formally, an ADT may be defined as a class of objects whose logical behavior is defined by a set of values and a set of operations. What is the thing about object-oriented programming that makes it beautiful? It is the combination of the data with the procedures that operate on the data. Right? Good. So, an application programming interface, or API, is an interface between different parts of a computer program intended to simplify the implementation and maintenance of the software. So basically, if you have a class, the methods of that class are its API. In this case, let's see, to specify the behavior of an abstract data type, we will use an application programming interface. In C, this would be something like the collection of the function prototypes in the file that we're working on. In this case, APIs are a list of constructors and instance methods or operations with an informal description. So, the API is a fundamental part of the documentation of any piece of software that is expected to actually be used by people. So, you know, it's not sufficient to just have the name of the function hanging out there. You also have to describe what that function is doing to the people who may want to use it.
Would this be Python's magic method or no?
I don't know if I'd consider Python's magic method. Like, they're certainly part of the API to, like, the person writing the, like, I guess it's an API between the person writing the class and Python's prelude. It's like, where's the interface, right? So I would say, like, certainly, you know, but at the same time, the magic methods can be used by people using the class. So it's also how to access the class from the user of the class. So both of those things, I guess. Python's terrible. Let's not talk about it as much as possible. So, at this point in the lecture, this is, wait, is that clock fast?
No, it's accurate now.
It's accurate now? And I was counting on it being slow. Anyway, so, this will be a preview of coming attractions. We are going to, in the next class, discuss 3 different types of data structures. We will talk about bags, stacks, and queues. Thank you very much.